All right. Good afternoon, everybody. For those of you who are listening in from Houston, it's my great pleasure to introduce today's speaker, Professor Piers Coleman at Rutgers University. Let me say a few words about Piers. He, as you know, he's a British, so he started his undergraduate career at Cambridge University, in fact, at Trinity College. And then he tells me the story how I wasn't sure if you sailed across the Atlantic to go to Princeton, or did you take a plane and then your grandfather's clock floated? That was like,
no, I took a boat.
You took a boat. Okay, so this puts it into perspective, right? So Piers literally took a boat to take a PhD position with P.W. Anderson at Princeton. 3 or 4 years later, he continued with a postdoc where he went to the Institute for Theoretical Physics, ITP, or now it's called Kavli Institute in Santa Barbara. And there he worked under the guidance of Bob Schrieffer. Upon completing that postdoc, Piers moved to Rutgers, and he went through the ranks. And he's a professor, and he's been there. In addition, Professor Coleman also holds a title at a position at Royal Holloway, University of London. And he organizes a marvelous series of summer talks called Physics in the City. I'm not sure in the COVID situation, I think you still did it, right? But it was
Physics in all the cities this last summer.
Right. So even better title. Piers is known for his many contributions to condensed matter. For those students of mine who are taking the solid state course, I highly recommend to them the physics the physics book, the Introduction to Many-Body Physics that Piers published a couple of years back, and I find that book very useful. I won't list all the accolades that Piers has. Let me, on a more personal note, say that because I had the pleasure of working as a postdoc under Piers's advisee, I could tell you many personal anecdotes, but I'll leave. Maybe those should be better reserved for when we meet in person over beer. But let me say once. I remember once sweating about whether we should put a certain interpretation into our paper, and I remember Piers telling me, "Well, Andre, you should remember, the fear of being wrong or being proven wrong should not stop a theorist from making a prediction." And so I'd like that to be maybe a prologue or a suitable prologue for today's talk. And welcome, Piers. If you'd like to share your screen.
Okay.
And today, Piers is going to tell us the story about the challenges, dark matter challenges in condensed matter. Piers, you're muted, but yes, now we can see your screen.
Okay, now you can see my screen, and we are going to go off to the races. Okay, well, thank you for inviting me down to Rice University. I would prefer not to be zooming in. It's a place that I have many friends, and I've always enjoyed my visits down to Houston, and I look forward to the next time I can come. In the meantime, let's do the best we can with this Zoom connection. I've got a talk here, which is the dark matter challenges of the solid state. And I invite you to interact with me, to ask me questions, to interrupt. I'm not looking at the chat. So Andre, you're going to be in charge of interrupting with urgent questions or even not urgent questions.
I can certainly do that.
So please do that. Okay. So I wanted to, so today's talk, let me first tell you, is a result of my collaboration with many people. I want to particularly highlight some of my most recent collaborators, Po-Yao Chang, Ona Erten, and Alexei Svelik, but also these other folks who are listed here, and there are some nice pictures of various people here, and some of their names will come up in this talk. And also a whole cast of characters who I've talked with over the years. So let me get down to business and tell you about my talk. So I'm going to spend a good half of this talk talking really with a more philosophical bent. when you do theoretical physics, probably when you do experimental physics, a lot of the time you spend is with failure. Things don't work out. And so one of the things I love to do is to look back at the historical record and try to understand how it all fits together with what we're trying to do today. And so that's what I'm going to talk about in the first part of this talk. And then I'm going to illustrate that a little bit with some of my own attempts to understand some of these dark matter challenges of the solid state. It's really an ongoing story. It's incomplete and there are failures there. But I'm going to particularly introduce you to two concepts that have affected my recent research, the notion of topology and the notion of fractalization. So those will be the subject of the second half of the talk. Good. So let's move on. Okay, so everything begins with Newton. Now, you may think Newton is a very, very long time ago, but actually it's only about 400 years ago that we all started thinking with this Renaissance approach to science. And one of the things that Newton was able to do was to understand the world in the lab by studying the cosmos at large. And more recently, this approach has been reinforced, shall we say, by the discovery that when you study stuff in the lab, you can also get ideas about the cosmos at large. And one of the stories that I'm going to tell you today is a little bit about how the ideas about why superconductors levitate strongly influence Higgs and led to our current understanding of electroweak theory. So this being the case, what I want to emphasize, and what I'll be talking about today, is how this connection, the deep link between the lab and the cosmos, is true today, and that the ideas that we develop in cosmological physics and astronomy are also important as conceptual ideas that work inside the inner universe of quantum matter that we play with in the lab. So let me take you back 100 years, 120 years. Let's talk about where things stood at the end of the 19th century. There were many early signs of the quantum age. For example, the very simple question of why do hot things change color? Why is matter so hard? Why don't we just fall through the ground since matter's mainly empty space? And why does the sun shine? These were very simple questions that could not be answered by physicists at the end of the 19th century. And they were the signs of a quantum revolution to come. And perhaps the take-home message here is that when you have a plethora of unanswered questions, it's a tremendous opportunity for revolution. So let's look at some of these questions. Why do hot things change color? How was that answered by quantum mechanics? Well, it led to the concept of black body radiation and the discovery of the photon. But it involved a huge cast of experimentalists and theorists working together to get to that point. A cast that began with the early studies of Kirchhoff and Wien, Raleigh's attempt to understand black body using classical mechanics, all the way up to Einstein's interpretation of Planck's result in terms of the concept of the quantum of energy, the photon, okay? Let's look at the next question that came up on our list. Why is matter so hard? We don't often think about this, but matter is incredibly hard. And what's the origin of it? Well, the understanding of why matter is so hard grew out of the study of atomic emission lines, leading ultimately to the Pauli exclusion principle, which is the origin of hardness and chemical diversity. And Wolfgang Pauli made this comment to Schrödinger about 100 years ago. He was depressed that beloved bosons didn't explain electrons, but the idea of Fermi-Dirac gave the explanation of the paramagnetism of metals. And of course, it's this exclusion principle that leads to the hardness of matter, because when we bring atoms together, we force electrons into the anti-bonding state, and this pushes very hard against the system and causes the repulsion. And so the exclusion principle drives the hardness of matter. And of course, we encode that in terms of the algebra of field operators, the fact that fermions anti-commute as field operators. Okay. And let's look at this last one. Why does the sun shine And why did it shine so slowly? Lord Rayleigh made an estimate of how long the sun would have been shining, and he was very proud of himself. But the geologist told him that the age of the rocks and the fossils was far longer than his estimate. And so this led to a big discrepancy. And of course, the origin of this is that the light from the sun is driven by nuclear fusion. And the rate limiting step is the combination of protons together to give deuterium. This is the rate limiting step. It's driven by the weak interaction. And inside the sun, a typical proton hangs around 9 billion years before fusion, which means that most of the protons are still waiting, which is fortunate for us. So why is this such a slow process? Well, it turns out that to understand this slow process meant that one had to understand why the electroweak interaction was so short range. And the resolution of this came from an unlikely direction, understanding the Meissner effect. Understanding the Meissner effect led to the understanding of how the magnetic field, or more generally, the electromagnetic field, is expelled from superconductors. And it led to this notion of how a gauge field acquires mass. Okay, this was first recognized in the context of superconductivity, but later on was generalized to the Higgs condensate. Is there a question there? The Higgs condensate, which is a condensate of spinors. And in fact, you can see the commonality between the two. The penetration depth of a superconductor is about 10 to the minus 7 meters. The penetration depth of the electroweak interaction is about 10 to the minus 18 meters. And this ratio of 10 to the minus 18 to 10 to the minus 7 gives us a way to estimate what the mass of a photon inside a material is. And it comes out just about right, 1 electron volt. Okay. And so, and there's a nice picture of Anderson and Higgs. Higgs actually remembered Anderson in his paper. He said that his speculations on gauge invariance and mass were all instrumental in putting together what we now know as the Anderson-Higgs mechanism. Okay. So in each of these cases, laboratory-based studies were used to reveal deep new concepts that apply equally to the laboratory and to the cosmos at large. Okay. So of course you might think, well, that's very well, but why should there be any link between the deep physics of the cosmos and stuff going on in a chunk of metal in my laboratory? And one of the reasons to believe that there may be close links is because of a notion we call reduction, we call emergence. Let's talk about that before we go on, okay? And really it's a concept that links our various fields of physics together, okay? Of course, when we think of frontiers of physics, we often think of the very large and the very small. And that's because in our DNA as physicists is this deep connection with the idea that we can understand nature by learning the laws that govern its smallest components. Okay. On the other hand, there's another approach, and of course, those laws have done us very well. We can understand the periodic table, for example, in terms of the laws of quantum mechanics and the exclusion principle. By contrast, we have other tables, for example, the standard model of elementary particles, which involves leptons, quarks, hadrons, the ZW and photon. We don't understand the underlying physics beneath that, okay? And that's really because once we get below 10 to the minus 18 meters, we don't know what happens next, okay? Now, from the point of view of the condensed matter physicists, we really understand physics very well on scales of order, the angstrom, which is the atom after all. And so you might think that we can put everything together and understand everything. That's a reductionist viewpoint. But in reality, that's not the case. As we put matter together, fascinating things that we didn't expect come to pass. And for example, we discover that there are new kinds of metals, new kinds of phase transition. Superconductors levitate, and nowadays we have even room temperature superconductors. And we get emergent processes such as crystallization, the formation of snowflakes. And this continues on upwards. For example, and to illustrate some of the problems we have, let's look at two examples. A Cooper pair in tin can be understood in terms of the BCS theory of superconductivity. It's rather interesting, though, because the physics of a Cooper pair is governed by a bound state which has an extent of about 230 nanometers, okay? So we understand physics up to 230 nanometers from the point of view of superconductivity. But here's another object with a diameter of about 250 nanometers. This is Mycoplasma mycoides, and this bacteria lives inside your gut, okay? And it's self-reproducing. It's an example of life. And we have no idea of the microscopic principles that govern life, how it evolves, what are the organizing principles. We really have a very experimental approach to this. Of course, we understand DNA, but the true organizing principles of life are still fully to be discovered. And this emphasizes the point that between the angstrom and the micron, we have a gulf that we are still coping with. And this is the gulf of emergence. And it raises the question, what are the principles that govern the emergence of collective behavior in matter between the angstrom and the micron? Okay. So these are principles of physics, and they are really in counterpart with the reductionist approach that is also very, very important to us. And it's really the convection between these two viewpoints that drives our field, okay? And the frontier is, of course, the very small and the very large, but also the very complex. And we have reason to believe, based on the past, that studies of emergent phenomena and lab scale phenomena in our lab may give us insights into principles that we are currently lacking to understand the cosmos at large, okay? And so that's a backdrop to what I'm going to talk about next, which of course are the questions that face our community as a physics community today. And of course, I won't be exhaustive, but it's really to illustrate the point. Let's now talk about some of the big challenges of the solid state. And I call them dark matter challenges of the solid state because I truly believe that their resolution will give us insights into quantum physics that we may need to understand the greater picture. So dark matter challenges of the solid state. And of course, here is a picture of gravitational lensing by dark matter. And dark matter, of course, is the fact that 94% of the background mass energy density of our vacuum is unaccounted for. We really don't understand the vacuum we live in. We don't understand, for example, also the fact that 0-point motion of the gravity of the electric field, the electromagnetic field, doesn't seem to gravitate. And we don't understand, we seem to know from various observations, what this background of energy and matter actually is. We believe that 24% may be composed of particles, ephemeral, ghostly particles that we haven't yet seen interact with us. We also believe that another 70% gives rise to a cosmological constant. It's 70% dark matter, okay? And no one can deny that this is a major challenge to 21st century physics. It signifies one of the big open holes in our understanding. But that's not to say that this is the only frontier, okay? And I want to show up another very simple thing that we don't understand today. It's the linear resistivity of strange metals. And I want to talk about them a bit, okay? This is exemplified by the cuprate superconductors discovered now 30 odd years ago in the 80s. And from the very beginning, it's been understood that these systems exhibit at their optimal doping a linear resistivity. That linear resistivity in the case of, this is lanthanum cuprate, can be seen to extend all the way from the point where the crystal actually melts right down to the superconducting transition temperature. Okay. And this signifies the breakdown of our understanding of metals in terms of electrons or quasiparticles. And we call that the breakdown of the Landau Fermi liquid. Let me show you another topic, which I will talk about in more detail in this talk, which is Sumerium Hexaboride. This is a material which is a metal at room temperature, but becomes an insulator at low temperatures. This material has been of great interest because it turns out to have topological properties, and I'll tell you about those. But most recently, it seems to also exhibit very strange behavior. It seems to have a Fermi surface. It exhibits the diamagnetic properties of a metal and exhibits oscillations, quantum oscillations in its diamagnetic susceptibility, and yet it's an extremely good insulator. Okay, and these and many other examples, some of which I'll expand on in a moment, suggest the potential for qualitatively new advances in our understanding of laboratory-based quantum matter. Okay, let me tell you a bit more about some of these mysteries. The cuprates are not alone. So before I do that, let's talk about where we are in this universe of quantum materials. Quantum materials, the map that we navigate in is, of course, the periodic table. And here I'm showing the central rows of the periodic table, and they're organized according to their degree of localization of their partially filled shells. And so 5D is more delocalized than 4D, and the most localized orbitals are the 4Fs. And so it's been organized this way. And one of the things that happens when you organize things this way is that you see a contrast between the fact that in the bottom left-hand corner, the electrons behave like waves. But in the top right-hand corner, the electrons in the partially filled shells actually localize and behave magnetically. They form local magnetic moments, okay? And so between these two extreme limits, there's this interesting region where there's a crossover. And these regions here, the electrons are on the brink of localization. They're on the brink of magnetism. And it's this region where we have very interesting behavior going on. These are electrons at the brink of localization, and these square boxes identify a number of interesting elements whose compounds seem to show fascinating behavior. From these rare earth materials, these actinide materials, iron and copper, and most recently studied iridium, all of these systems exhibit physics where the electrons are on the brink of localization. And at this point, the electrons are neither well-developed coherent waves, nor are they well-localized magnetic moments. And it's from this well that fascinating behavior seems to occur. So new kinds of quantum matter develop at the brink of localization. This isn't the only story. We can find other ways of localizing electrons. Perhaps the most recent example would be twisted bilayography, but we can do it in various ways. We can do it inside cold atoms, traps, okay? So one of the interesting properties that develops when you tune these systems to the brink of localization is that you see the emergence of this strange metallic behavior, this linear resistivity. Here it is in cerium cobalt indium 5, which is a miniature high temperature superconductor. And you see this linear behavior of resistivity over a huge temperature range down to the lowest temperatures. When we analyze this physics, we come to the conclusion that the linear resistance can be associated with a transport scattering time, which is the mean time between between scattering events from the point of view of Drude theory, which behaves as 1 over the temperature. In fact, we call this time the Planck time because it's the time associated with the uncertainty relation that goes with thermal fluctuations. And it's true to say that nobody understands why the scattering rate is scale invariant, governed exclusively by the temperature and nothing else. But one of the ideas that we have is that this is because each of these systems are close to a quantum phase transition. In fact, not just a quantum phase transition, but a quantum critical point. A quantum critical point is a point where a finite temperature phase transition has been squeezed to absolute zero. And when TC goes to zero, there's no heat left in the system. There's no thermal fluctuations left, but there are still 0-point fluctuations. And these 0-point fluctuations are, of course, when they grow, they destroy magnetism. They destroy long-range order. They melt the underlying quantum order. And at the point where things melt in metals, this is where the linear resistivity is seen to develop. And there are many examples. Here's another example. This is an iron-based superconductor tuned using phosphorus to a quantum critical point. And you see the resistivity is linear in temperature. And interestingly enough, you can field tune this system. And when you do so, the field replaces the temperature. And so all these things suggest a state of matter which is free of any apparent scale. It may be universal, but at the moment, we don't actually understand what the nature of this quantum critical point is. Okay. And of course, one of the fascinating things of these quantum critical points is that they're frequently associated with superconductivity. And the cuprates, the iron-based and the cerium-based systems all exhibit apparently superconductivity close to a quantum critical point. In this case, the cerium systems, you can actually reveal that quantum critical point using a magnetic field. In the case of the cuprate superconductors, you need 50 or 100 Tesla to destroy the superconductivity. And so it's still an ansatz that beneath the dome, there is a quantum critical point, but I think it's fairly well believed. So these are an example, this represents a cross-section of some of these unsolved problems of the solid state. And so these represent and suggest the potential for qualitatively new advances in our understanding of quantum matter. And I think they should be regarded as the other side of the coin to the dark matter challenges. And so what are we doing to understand them? Well, we're developing new kinds of experiment, but we're also developing new ways of thinking about quantum systems. One of the words you'll hear is the word entanglement. And there's the question of what kinds of correlations, what kinds of entanglement are there amongst the spins and the electrons? We're studying the possibility of new kinds of quantum phase transition. As I mentioned earlier, these are phase transitions driven by zero-point fluctuations. There is an interest in new kinds of broken symmetry. But today, what I want to focus on in the remaining part of the talk are two issues, the words topology and the words fractionalization. I'm not sure whether I'm going to get to the end of my talk, but if there's one takeaway, I think these are two central concepts that are driving the field today. And I'll try to illustrate how with some small examples. In fact, one material, this material, Sumerium Hexaboride. Any questions? How long is this going to go on? Okay, let's go. All right. So as in the past, phenomena in the lab and the cosmos are likely to be linked. Okay, so let's talk about that. So I want to talk about a collision of concepts, topology and fractalization. Let's talk about topology a little bit, the rise of topology. And one of the things that is often said is that you can gain new insight into physics by revisiting areas that are thought to be closed. And the case of topology is a very nice example of that. This is also an issue which is very important for funding agencies to understand. It's not sufficient just to work on the trendy areas. Sometimes you have to go back to things and say, did we understand them properly? So here's a nice example. In 1939, one of the co-inventors of the transistor, Bill Shockley, did a very nice calculation. This was a calculation using computers of the day. Computers of the day were women who had handheld electric calculators, and they would hand their results to their neighbor and pass them along. And that was literally how this calculation was carried out. It was a calculation on a one-dimensional non-interacting lattice consisting of 8 atoms, okay? And this is the model. It consists of an S band and a P band. And as you push the atoms together, those bands start to broaden. And you can see something interesting happened. When the bands crossed, they actually produced this split-off state, which is actually an edge state. And this is an example of the effect of crossing two atomic orbitals of different parity. And Shockley understood this reasonably well for the time, and he noticed that there was a link between the bulk and the boundaries, and he thought that this link would extend to higher dimensions. And he suggested that diamond would have similar surface states. And you can read it in his PhysRev from PhysRev 1939. But what he was missing is the role of topology, and in particular, the important role of spin-orbit coupling. So the rise of topology had to wait many new developments. And of course, from the mathematical point of view, the ideas of topology have been around for a very long time. And one of the key ideas is that you can understand topology using differential geometry. And one of the key equations, key relationships determined by Gauss and Bonnet in the 19th century was that when you integrate the curvature, the Gaussian curvature, over the surface of a system, it tells you the number of handles, 1 minus the genus, okay? And so this is a nice example of how topology is linked to differential geometry. But what we now know today is that differential geometry of the wave function can lead to a topology of insulating and gap phases, which we know of as topological phases. And how we got to there was a very windy path, okay? And it began with the study of the integer quantum Hall effect, and also the study of superfluid helium-3. And both of these systems are fully gapped systems which have an underlying topology in their wave function. It wasn't until this century that it was appreciated that this had implications for insulators. And one of the key ideas developed by a cast of characters that include Berry and the late David Thouless, was that inside matter, in momentum space, there is a kind of synthetic gauge field. It's called the Berry connection, and it tells you how the phase of the block states winds around in momentum space. And the textures of this phase determine the novel topology of a ground state. Okay. And once this was realized, it was realized you could extend it to systems with strong spin-orbit coupling. And this wonderful cast of theorists and experimentalists here were part of this new revolution of the rise of topology. And it led to the realization that band crossings can wind up topology of a wave function and lead to a new class of insulator, which we now know as the Z2 topological insulator. What's the cartoon understanding of a Z2 topological insulator? Well, it's the following. We can think of conventional insulators as really being adiabatic continuations of the vacuum, in the sense that you take a conventional band insulator and you gradually pull it apart, nothing happens, everything remains localized, and you can adiabatically go to the very, very dilute sample. However, if we cross two electronic states at a high symmetry point of opposite parity, like this, okay, then it turns out that they're supposed to cross, but they haven't. It turns out that when we do this, that we twist the topology of the insulator. And now there's no way to go adiabatically from the insulator to the vacuum without closing the gap, because they have different topologies. And what this means is that the surfaces inevitably have to be metallic. And what happens is that the surfaces, you develop relativistic electrons with a Dirac spectrum. This is our current understanding, okay? This is now the new normal, okay? And what it means literally is that if you take an insulator and you drive the states at the high symmetry points to cross through one another, if they have opposite parity, then by crossing them through, you kind of wind up the topology of the ground state as like winding up a Mobius strip, okay? And that new insulator has these gapless Dirac cones at the surface. So how can you wind this up? Well, you can change the spin-orbit coupling, you can change the chemistry, it's a whole black art, but in between the two, there is a phase transition. It's a topological phase transition. And this whole area of conceptual understanding has driven a whole new world of material research. and has led to the discovery of Z2 topological insulators, both two-dimensional and three-dimensional. Okay, but in that new world, we now have the possibility of a collision of concepts, because what we'd like to do is ask what happens when we take into account the effects of interactions. Okay, what happens when we mix these new rules and principles of topological quantum matter with strong correlation? And there's a belief that when we bring these two things together, we'll have many new developments. We'll have the possibility of new kinds of device, new forms of matter, new kinds of excitation that may be useful, for example, for quantum computation, such as Majorana fermions. And when topology and broken symmetry come together, we may have new kinds of order. We already know a little bit about this because, for example, the fractional quantum Hall effect is an example of a new form of topological order. But what about other materials? What happens if, for example, we try to find topological insulators that are very strongly interacting? Okay. And so that was something that I got involved in, and I'll tell you about in the last 10, 20 minutes of this talk. So one of the questions is, where should you go in the periodic table? So these conventional Z2 topological insulators are typically built by using a mixture of S and P electrons. These are weakly interacting, okay? And so what we were interested in about 10 years ago was, could there be 4 or 5 F electron counterparts? And the interesting thing is that an F electron, like a P electron, has odd parity. So if you can get it to cross with, say, a D state with, say, a D state or an S state, you should be able to drive a topological phase transition, okay? And the advantage of these 4F electron systems is that they're strongly correlated. They have very large spin-orbit coupling. They have odd parity. And they're also simple in a kind of weird way. The topology resides in the hybridization between these localized orbitals and the surrounding electrons. And here is a list of a very partial list of systems that may be topological. And I'm going to concentrate on just one of these, which is Sumerium Hexaboride. Okay. So I'm going to tell you about that in the last 15 minutes of the talk, and how we thought we'd solved it, and then that led to a new mystery. Okay. So topology meets magnetism. And this is the curve I showed you earlier in the talk of the resistivity of Sumerium Hexaboride. This resistivity curve was measured in 1969, which was the year that Ted Jabal moved from Bell Labs in New Jersey to Stanford University in California. And I'm proud to say that Ted is still actively doing physics today as he approaches his 100th birthday. So this is what they found, this rise of resistivity, but also mysteriously, as this small insulating gap forms, something else happened. So in a very, very naive way, you can kind of understand the physics of this Condo insulator in using a very, very simple Hamiltonian, which is known as the Condo lattice model. And I won't be writing many formula in this colloquium, but here is that model just for interest. And to understand this, this is electrons buzzing around, interacting with a lattice of local moments via this super exchange, this anti-ferromagnetic interaction. And the seat of the pants cartoon understanding of this problem is that actually this J becomes inevitably very, very large at low temperatures. It renormalizes the strong coupling. So you can basically cross out the kinetic energy of the electrons and treat this as a whole bunch of singlets, okay? And this is a very interesting problem because even though the band is half filled, the spins force it to become a band insulator. In some sense, they behave as spin-a-half excitations. And if you look at it very carefully, this is an example, an early example of spin fractalization. Spins thinking they're fermions, because when you flip one of these local moments, you actually create a pair of quasiparticles, okay? So we were interested in this problem, asking what is the interplay of topology? And now we're going to ask, what is the interplay of topology with spin fractalization? So at one level, it may just be a simple topological insulator. In fact, the early data of Jabal et al. And later Batlog and Allen showed a resistivity plateau at low temperatures. And this piqued our interest. Could this be, in fact, due to topological surface states? And so this led us to write a paper in 2010 speculating that systems like this might be topological, but strongly interacting topological insulators. And here's the basic idea. This is the band structure of Sumerium Hexaboride. It contains a band of d electrons and a narrow band of f electrons. And when you poke this d band through the flat band here, you inevitably get a crossing between an even and odd parity state at the x points, which means that you should get 3 surface modes, 3 Dirac cones on the surface. And it turns out this simplistic viewpoint is borne out by experiment. For example, you can do measurements on the, before I do that, let me just say that the model of this problem has a hybridization between the f electrons and the d electrons, which vanishes at the x point. And in the simplest model, you can write this hybridization as k dot sigma or sine of k dot sigma. And when you write that model down, it looks like this. This is the model that contains all the important physics apart from the interactions. And this model is very fascinating because actually it's really a miniature version of a Dirac Hamiltonian, okay? And you can think of the diagonal terms like a mass and the off-diagonal terms like the dispersion of the Dirac Hamiltonian. In fact, another model that has this same physics is the model of superfluid helium-3, which also has a Dirac Hamiltonian like this. And this model actually has topology because this hybridization, in fact, the gap function of helium-3 points outwards and forms a hedgehog around the Fermi surface. So this system forms a similar hedgehog around the high symmetry points, and lo and behold, that gives rise to conducting surface states. The Hall constant derives from the surface, and if you look at the conductivity, it all runs round the edge of the sample. This is beautiful work by Steve Walgast and others. And furthermore, when you do ARPAs, you see surface states. You even see different surface states depending on which direction you look at it. And last but not least, if you're very cunning, you can actually measure the bulk resistivity, subtracting out the contributions from the surface. And this was done in a beautiful work by Caligli and Kurdak. This is not the most up-to-date reference, in which they use a Corbino disk to extract the bulk resistivity using a scaling method. And from this, they were able to show by injecting the current in different ways that the resistivity continues to rise down to very, very low temperatures. And if you believe their data, the resistivity of Sumerium Hexaboride actually rises through about 8 decades between about 10 Kelvin and the lowest temperatures they went to. And so this is actually one of the world's most remarkable and robust bulk insulators. Remarkable given that the gap is about 20 Kelvin. And therein lies the mystery about it, because it's more insulating than it really ought to be. And so this takes me to the final part of my talk. In the last 5-10 minutes, I want to talk about fractalization. The fact that spins can break up into pairs of quasiparticles, okay? And why should we think about this? Because it turns out that not everything is good with our understanding of Sumerium Hexaboride. The bulk is anomalous, and let me show you some of the problems. It's electrically insulating, but it seems to host gapless excitations. Let me show you one example of that. This is the specific heat of this system, comparing lanthanum hexaboride, which has itinerant d electrons and no f electrons, with insulating Sumerium hexaboride. Notice that C over T comes in to be about 50 millijoules per mole Kelvin squared here. It's about 10 times that of the metal lanthanum hexaboride, even though it's a very, very good insulator. Here's another mystery. If you look at its conductivity at low frequencies, there's so much conductivity there. It's a DC insulator, but it's actually an AC metal down into the terahertz range. We'd love to know what happens at still lower frequencies. Okay, and the dielectric constant from an extrapolation of sigma to zero frequency exceeds 600. It's extremely polarizable. Okay, and here's another weird thing. At least in some subset of the data, it exhibits a thermal conductivity which switches on in a magnetic field, and it's linear. In it's kappa over T goes to a constant, a linear term here, as if there's something running around that carries entropy, even though it's a good insulator. And last but not least, these very weird data that suggest that there is a Fermi surface, which looks remarkably similar to the Fermi surface of lanthanum hexaboride. These measurements are done by torque magnetometry, and they measure oscillations. You can see them with the naked eye in the bulk susceptibility. So it's very difficult to attribute these oscillations to surface states. And so this paper claimed that they could be understood in terms of two groups of Fermi surface, a very large one and a very small bunch of pockets. Okay. And so the neutral Fermi surface of this system resembles that of D bands in lanthanum hexaboride. Okay. This is the conundrum of this material. On the one hand, it looks like it's a strongly interacting topological insulator. Okay. On the other hand, it has all these weird properties that suggest some kind of neutral Fermi surface. And so this has led to a marvelous playground for theorists, because we can all follow our inner tendencies and put forward various different theories. On the one hand, there are the theories that say, look, actually, this is a very narrow gap insulator. And when you apply a large field, it makes sense that you'll get a breakdown of that gap, and you'll start to see the quantum oscillations of the underlying Fermi surface. On the other hand, there's a group that includes myself, which says, no, this doesn't make sense. That won't explain the linear specific heat. And furthermore, you need a much higher field than is observed to produce the effects you're talking about. And so this is a theorist playground. I want to spend the last 5 minutes telling you about our crazy theory, okay? But from a practical point of view, it raises the question that maybe both viewpoints are right. Maybe there are two phases, two competing insulating phases with different kinds of spin fractalization. On this side, the spin fractalizes as a fermion. On this side, it does something different, okay? So we tried to make a theory of this, here are some of the works on the neutral fermion idea. Here is the excitonic breakdown theory of Noller and Cooper. And I would say that no one has understood the problem perfectly at this time. But our line of reasoning was the following. It was, look, these excitations exhibit conventional de Haas-van Alphen oscillations. They're neutral, but they exhibit orbital diamagnetism. This Lifshitz-Korsavich tells you that there's a Fermi-Dirac distribution. But weirdly, the quasiparticles do not couple to E, but couple to B. And the B that the experiment sees seems to be the external B. So how to resolve that? Well, the simplest way is just to cross out E in the Lorentz equation. That's great. You're now solved and you can now go forward. Unfortunately, that's not allowed because particles don't couple to E and B, they couple to the vector potential. And if they feel the curl of the vector potential, they also feel the time derivative of the vector potential. And that's what gives you the E term here. And so long as gauge invariance works, this pathway is doomed, okay? On the other hand, that's what the experiment seems to suggest. And so this led us to wonder whether this differential coupling to E and B might be a sign of some kind of breakdown of gauge invariance inside the material. Okay. And this led to the question, can we actually have broken gauge invariance without superconductivity? Let me just tell you in wrapping up here how we came to develop this theory. It's based on the idea of fractalization. So inside a Condo lattice and inside a Heisenberg chain, magnons fractalize into spinons or heavy electrons. These are kind of Dirac particles. But inside the Kitaev honeycomb lattice, spins don't fractionalize into Dirac fermions. They fractionalize into Majorana fermions, fermions that are their own antiparticles, a little bit like perhaps the neutrino of the cosmos. And so this raises the question, could it happen in the Condo lattice? Could the Condo lattice exhibit not only Dirac fractalization that gives you this large Fermi surfaces and the regular Condo insulator, could they fractionalize into Majorana fermions? And so we put together a theory based on that, and it led, this is the picture of the energy spectrum, assuming that spins fractionalize as regular fermions. Each fermion is 2 Majorana fermions, so you see 4 Majorana fermions connecting up to a conduction C, which also has 2 Dirac fermions per electron, which means 4 Majorana fermions. Everyone is happy. But if we now represent the spin by a Majorana fermion, it then is represented by 3 Majorana fermions. And so there's then a mismatch. The spin is 3, whereas the conduction electron is 4. And so there's a problem, and one of the conduction electrons gets left behind, and it leads to a gapless band of Majorana fermions. If you like, these are electrons and holes moving in the same direction that have been glued together into a single excitation, so they don't carry anything but heat. Okay. And so I'm not going to say much more about this. We were able to put together a theory based on this. It turns out that these electrons, although they don't couple directly to a vector potential linearly, they're not really neutral because they have a fluctuating charge. And so they couple to a squared, and this leads to a reduced form of Landau condensation. And just to finish off, it turns out that this state, by coupling electrons and holes in a weird way, is a kind of failed triplet superconductor. And the topology of this failed superconductor doesn't allow it to create persistent currents. And so this led to the prediction that we made that actually magnetic fields and electric fields can penetrate into this failed superconductor, forming an insulator. One of the predictions we had was that this would lead to a kind of skyrmion distribution of field and a texture of the underlying order parameter. And we deduced that at very low fields, perhaps below a Gauss, these skyrmions would disappear and you might see diamagnetism. So an experiment was carried out at the Tata Institute in India, and they discovered, in fact, that this doesn't happen. In fact, there's no diamagnetism at extremely small fields, and our theory doesn't work. Okay, so it's an elegant theory. We still believe that aspects of it are right, but we're not sure what went wrong, but we know it failed. It still raises the interesting question that you might have fractalization going on in a way we haven't fully understood. So the broader conclusions, history teaches us that physics in the lab and the cosmos are often intertwined. And I told you about a whole bunch of dark matter challenges of the solid state, which was by no means complete, which has the potential for qualitatively new advances of our understanding of quantum matter. And presumably, if we understand quantum matter better, we'll understand the vacuum better. And I finally ended up with Sumerium Hexaboride, an old mystery that brings together ideas of topology and fractalization. Thank you very much.
Let's thank Piers again. You could unmute your mics if you would. Thanks for a wonderful talk. All right, we do have time for question. Yi Chen, a student, please ask your question.
Thank you. I guess when you mentioned the gapless marijuana excitation, maybe it's just the signal is not bad, but I was wondering, I didn't hear the full part when you talk about because the internet connection, but I was wondering, is there any experimental features that can be shown by this gapless marijuana excitation?
Well, of course, any good theorist tries to make their theory match up with the data that's known so far. And so we tried very hard to do that. And so, for example, this Fermi surface of Majorana fermions would give a linear specific heat and would enable us to understand that aspect of the problem. But more generally, you could ask, well, wouldn't those particles, even though they don't carry charge, wouldn't they conduct heat? And in our simple-minded theory, they would conduct heat even in zero magnetic field, and that's not observed. However, we have speculated that, okay, so what other things would they produce? Well, they would produce a conductivity, because it turns out that the matrix element, their current matrix element is actually proportional to their energy. And so this predicts that you would then get a kind of Drude conductivity times energy squared, which would give you which when you average over the Fermi surface would give you another factor of T. And so if you could only measure the low frequency conductivity of this system, there is actually a prediction for the frequency dependence that you would get. It's like a thermal average of a Drude conductivity with a form factor that's linear in temperature or frequency. And so that gives you another power of frequency and temperature. That's one thing that could be checked if you could do low enough frequency measurements. But of course, the big prediction that we made, which was that this system might actually stop failing as a superconductor and become diamagnetic at low temperatures, that has failed so far. So we know that if this has got anything to do with the real world, something's wrong with our theory. We're missing something in it, okay? Or maybe it just isn't relevant to Sumerium Hexaboride. That still raises the question, what are all these anomalies coming from? And so we're still actively working on this theory. One of the interesting things that we've discovered recently is that we can actually stabilize this kind of spin by coupling our Condo lattice to a variant of the Kitaev spin liquid. And we're currently having a lot of fun because we've actually found a limit in which our theory actually seems to be controllable. Whether that limit gives us an explanation of Sumerium Hexaboride, I don't know.
I see. Thank you.
You're welcome.
Yeah, so I have a question, Piers, as mentioned. Yeah, so I was curious for the Sumerium Hexaboride. People see this, quantum oscillation from magnetization. So are there any other signatures of that? I mean, besides, the magnetization, measurement, are there, for example, thermal conductivity and other things that are indicating that you have a possibly,
well,
fractionalized,
Of course, in every story, there's always the untold story. The untold story here is that these samples seem to be very sensitive to preparation.
Right.
And you can thermally cycle them and the signal disappears. And for that reason, other groups haven't been able to reproduce them. In the meantime, what has happened is that the community has moved on to another group of bizarre insulators that also have quantum oscillations. And so, for example, there's the material ytterbium boron 12, which also exhibits very similar behavior, which has been extensively studied. And there are a number of other systems too that exhibit this behavior. It looks like that you need a finite field to switch on this physics. And it may be that in Sumerium Hexaboride, when you remove the field, you have an unstable phase that exists for a while if you don't heat it up, if you don't mess with it too much. So I think the good news is that there's a bunch of other materials coming online which show very similar behavior. Mm-hmm. And I think this new family of materials will give us the opportunity to actually study this and come to terms and figure out whether we need a radical explanation of the physics or whether we can understand it as some as yet real world aspect of topological insulators.
Okay.
Chimiao, please go ahead.
Yes, thank you. Piers, beautiful talk. I want to ask you about also this Sumerium Hexaboride side. So what is it? I mean, we know there are other Condo insulators. What is it about Sumerium Hexaboride that makes it special, or is it special among all the Condo insulators?
Well, there are other Condo insulators that behave in a more conservative fashion.
We actually know that the other Condo insulators are behaving in a conservative fashion.
Yeah, that's true. There is, for example, a very well-studied cerium Condo insulator, cerium platinum bismuth 343, in which when you apply a magnetic field, the gap closes as it should. You get a nice metal beyond that point, and there are no surface states. Everything is good. Okay. We don't have many other topological insulators of this class that we really know have reliable surface states. So it's very difficult to know whether the weirdness of this system is just because it's some aspect of it being a topological insulator, which would be the Noller-Cooper viewpoint, or whether it's because there's another phase there which is behaving weirdly and differently to a regular topological insulator. And so I think this is an unfolding story where you won't get a straight answer from people at the moment. We don't know enough. It's an area which could do with more experimental attention.
Piers, I wonder if you could comment on another example of fractionalization, which may speak also to the astrophysicists and high energy people in the audience. So often in two-dimensional, two-spatial dimension materials, one of the problems that arises is when you try to fractionalize the spins in terms of the fermions, is that you do it at the cost of coupling them very strongly to a gauge field.
Mm.
And as far as we know, we don't actually know how to solve a problem in 2+1 spatial dimensions of fermions that are coupled to gauge fields. And that's actually known as QED3. It's literally instead of 3+1 dimensional Minkowski space, we have a 2+1 dimensional space. And unlike what Feynman and Tomonaga and Schwinger and Gell-Mann did back, in the 1950s, we don't know how to do it in one dimension fewer. I wonder if you could comment on that aspect.
But what has that got something to do with fractalization?
In a sense that if the way that picture arises often is that you start from a frustrated magnet in 2D. There are
you get an emergent 2+1 dimensional electromagnetism coming about from that. Well, my first comment would be that thanks to the great work of Kitaev, we actually do have a nice example of a two-dimensional system with a gauge field, which we can study in detail. And you're right that for example, if you spin flip in that system, you create both quasiparticles and you create you create visons, you create defects in the gauge field. But I don't know. I mean, I probably can't comment too much on these other cases. Although, you wanted a remark that connects up with the world of particle physics. In a way, there is a connection here with the physics of quarks. Quarks under normal conditions are completely confined, and so the excitations that you have are just sharp baryonic states. However, if you take quark gluon matter and you compress it highly, you can actually transition to a regime where the quarks are deconfined. And at that point, you would regard the baryon as having fractalized. Of course, from the reductionist viewpoint, you say that we know that the baryons already had those particles inside them. And so it's no great surprise to us. But nevertheless, there is an important connection there. I think the fractalization, though, that we have in, say, the fractal quantum Hall effect, which is a nice example of a 2D system which exhibits fractalization, and the fractalization we have in spin systems are examples of fractalization that we didn't understand, even though we understood the microscopic physics. And so there are examples of emergent fractalization. Nevertheless, I think the mechanisms by which particles fractalize, for example, to get a heavy fermion, you have to form a fermionic bound state. We don't know much about fermionic bound states in field theory. And we don't know how they interact with broken symmetries. So I think that there are possibilities here for generalizations. It may be, for example, there are mechanisms to some of the fermions we have hanging around in our universe we don't understand, such as neutrinos, right? Maybe the reason we don't understand them is we don't understand some of the mechanisms that are possible in generalized field theories, such as fermionic bound states. But we have those in condensed matter physics, and maybe we can take them and generalize them and understand them in a cosmic context.
Anybody else has a question? Shall we give them 42 seconds? So
I want to know when Zoom is going to develop a method for us to share drinks so we can all have a drink or a beer after a talk like this. Unfortunately, that technology is not yet there. Maybe we should start a company.
That would be the alcohol transfer protocol. It's the
Yes.
rare part of the internet that you don't hear too much about.
Beer as the emerging object.
Yeah, a non-Fermi liquid.
Well, if there are no questions, let us do the following. Let us conclude this formal section. I'm going to stop the recording. And by tradition, we ask the speaker if, Piers, you wouldn't mind hanging around, and if students or faculty or anybody has any burning questions, they could ask it informally.
Yep.
And before we do that, let's thank Piers once again for the wonderful talk.
Thank you for inviting me, everyone.